Hello everyone and welcome back. So in today's video we'll be discussing about activation functions. We will explore some of the common activation functions we have and the major role they play in neural networks. So for this and more, grab your notepads and let's dive into it. So before we jump into the types of activation functions, I would like us to understand the purpose of activation function. So activation functions are the mathematical equations that determines the output of a network node. Okay, so they kind of introduce some non-linearity in the network, which enables the network to learn complex patterns in data. Okay, so the diagram here, as you can see, is a neural network node being applied to or connected to an activation function. Okay, so we have three inputs with their width and we have a bias. Okay, so the output of this node is then applied to an activation function, and this activation function is going to determine the output of the network node. Okay, so that is basically how activation function works. I would like us to now look at some of the types of activation functions we have. And the first one I would like us to talk about is the Sigmoid function, also known as the logistic function. Okay, so it's basically squashes the input value between 0 and 1. Okay, so that's what activation function or the Sigmoid activation function does. So when you apply your inputs, okay, it takes the input and no matter what the value is, it squashes it between 0 and 1. Okay, so that's the function of the activation function, and it's basically used in classification taxes. So let's say after the activation function, you just have to write some algorithm to check if the value is 0.5 or above, then it belongs to class A. If it's below 0.5, it belongs to class B. Okay, so that is how it's used in classification tax. But in some way, it suffers from vanishing gradient problem. Okay, making it less suitable for deep neural network problems or tax. Okay, so the next one I would like us to talk about is the hyperbolic tangent function. Okay, so it's also similar to the sigmoid function, just that this time around the input is now squashed between -1 and 1. Okay, and it overcomes the limitation of the sigmoid function, and it's commonly used in hidden layers. Okay, yeah, so when you apply the output of the node is being applied to the activation function, the output must definitely be between -1 and 1. Okay, so that is for the hyperbolic tangent function. Now the next one I would like us to talk about is the rectified linear unit, which is termed as ReLU. Okay, so with the ReLU function, what it does is it takes in an input. Okay, and if the input is positive, it gives us that same value as an output. Okay, but if it's negative, then the output will be 0. All right, so as you can see the diagram here, when you apply a positive value, you get the same positive value as your y, right? But when you apply a negative value, you get 0 as your y, right? Back again here, let's say after the computation, we had 10 as our output from the node and being applied to activation function. The output will be 10, right? But when we apply, let's say -10, the output will be 0. Okay, when you apply -1000, negative infinity, the output will be 0. Okay, so that is how the ReLU works, and it comes along with a problem which is termed as the dying ReLU problem. All right, so let me take a second to explain the dying ReLU problem to you. So let's go back to our diagram. Okay, so let's say this, after the summation here, the value is always negative. Then it means the output will be always positive, 0, right? And that is termed as the dying problem. Okay, so it means this node is dead because always, no matter what, the output here, the end result is 0, right? So that is the challenge when it comes to ReLU. Okay, so they try to get another function that solve that problem, and that function is the Leaky ReLU or the Leaky Rectified linear unit. Okay, so what this one does is that it tries to apply or allow some small positive gradient in the inputs. Okay, so let's say you apply let's say -10. Okay, so instead of giving you 0, it gives you, let's say, -2, -5, right? Yeah, so that is for the leak or leaky ReLU activation function. And the last one I would like us to talk about is exponential linear unit. Okay, and it's also another variation of the ReLU, which avoids the dying ReLU problem. Okay, by allowing some negative values. So as you can see here, we have some negative values right here. Okay, but this time around, it introduced some exponential components in the negative inputs. Okay, which smoothens the transition. All right. Yeah. So these are some of the activation functions we have. Okay, and each of them has its own weaknesses and strength. Okay, so the choice basically depends on the characteristics of your data set and your architecture network. Okay, so I hope you enjoyed this video. If you did, kindly click on the subscribe button, like this video, share with friends, and see you in the next one.